In this video, we will talk about what a connected graph is and what a disconnected graph is. So a graph is connected if there is a path between any two distinct vertices. And if there isn't, well, then it's called disconnected. So let's do an example. Let's determine whether the following graphs are connected or disconnected first, and then we'll talk about the second question about connected components. So I got these two graphs. So if I look at this first graph, well, I notice that, for example, there's no path from A to F because there's no edges connecting. It's somehow connecting those two that it would lead me from A to somehow get to F. So this first graph is disconnected. And there's many examples of that. There's many examples of two vertices I could pick, like C and G, where there's no path between them. So this is disconnected. And one example, e.g., is, well, there's no path. There's no path between A and F. That's just one reason out of many that this is disconnected. Okay, what about graph 2? Well, it's easier to see that in graph 2 that no matter which two vertices that I pick, there's a path getting me from one to the other. That's going to be true no matter which two vertices I pick. Like if I pick these two, I could take this path to get from one to the other. So this graph is indeed connected. This is connected. There's a path between any two distinct vertices. So, okay, the second part of the question now asks, how many connected components does each graph have? So instead of giving a formal definition of what a connected component is, I think it's just easier to describe what it is conceptually. If we think about this first graph, well, even though it's disconnected, how many pieces does it have that themselves are connected? And, well, there's 3 of them. It has 3 connected components, 3 connected pieces that it's split up into. And one of those pieces is AB. AB is one piece. One piece is, well, this set of 4 vertices, C, D, E, F. And then finally, I got this isolated vertex, G. That is a connected component. Okay. One thing that you might be wondering is, well, to be connected, if I think about G, shouldn't there be a path between any two distinct vertices? And if I think about this component here, well, there's no edges at all. So how are there any paths to connect anything? So, the reason why it's connected has to do with a subtlety in what this definition is saying. So that definition, I'm going to write it to the side, is saying that if we have two distinct vertices, let me call them X and Y. If X and Y are distinct vertices, the definition of connected says, well, then there's got to be a path between them. Then there is a path. I'm just going to abbreviate between them. Okay, and if I think about G, just G by itself, well, there aren't two distinct vertices there. There's just one, which means the if part of this if-then statement is false. This if part would be false if we are just talking about G by itself. And we've seen that if you have an if-then statement and the if part is false, that automatically makes the whole thing true. So the if part is false means the whole thing is true. The whole thing is true. So we are tying this back to our logic chapter, way back when in chapter 1 here. Okay, so that's why G is indeed connected. It does satisfy this definition. Okay. Graph 2, well, because it was connected, it just has one connected component. One connected component. So typically we only use the term connected component to refer to graphs that are disconnected, because the ones that are connected, well, they're already connected. They just have one connected component. So I want to note that a graph is a union. Any graph is a union of disjoint connected components. For example, graph 1 is a union of the components A, B, C, D, E, F, and G. Those three things put together, if I union them, that makes up my graph, this graph 1. So I'm going to end with an example. How many disjoint connected, this should say connected. Let me fix that. Connected components does the following graph have? So I got this graph here. Well, so if I think about it, well, okay, there's this triangle AEC. Let me just draw that to the side. So there's this triangle AEC, A, C, and then E. And then there's this other triangle B, E, and D. Let me put that in a different color. B, F and D. I just misread it. B, F, and then D. B, F, and then D. And in fact, one of the things that I'm allowed to do with a graph is I can move the vertices around. So I can move these three vertices around, that second triangle that I point out, and just shift it over to the side like I did here so that it completely separates from the first triangle. So in fact, the way that I've drawn these two triangles over here, this is actually the same graph. It's the same graph. We just moved the vertices around. And we've seen before that that is a totally legal thing to do with a graph. We just moved the vertices around. And by moving the vertices around, it makes it easier to see how many connected components there are, because now it's clear, well, there's two of them. There's two connected components. It's just each of these triangles that we got. Two connected components. And there we have it. So in the next video, we will talk about what are called bipartite graphs.